Good afternoon, students. Am I audible? You see, we have already completed that canal design process for mobile boundary. Okay, so today we are going to discuss the process for designing canal. Good afternoon, students. Am I audible? Okay, so today we are going to start our new chapter, or you can say our second unit is our design of canal, or you can say design of channel. Okay, so here we have two types of channel. One is your erodible, and one is non-erodible. Okay, okay. You can see here types of channel to be designed. We have two types. One is erodible or mobile boundary channel. Okay, one is non-erodible or rigid boundary channel. That means suppose we need to construct a canal, okay, a irrigation canal of trapezoidal channel. Okay, then first we have to do the artwork. Okay, and we okay. So you see this is what is made up of art. Okay, so this is your mobile boundary channel or erodible channel. That means when there is a flow of water, there must may be some erosion because of the velocity of water. So that is why it is called erodible or mobile boundary. Okay. So if we do, or if you lay down some brick here, if you lay down some brick, okay, or you can say brickwork, if we lay down some brick and then we do plaster, okay, then okay, okay. So then this channel becomes not erodible and rigid boundary. Now this boundary of the channel is rigid. Okay. So this is called line canal. Once you do brick work or you do use some kind of motor also, if you fix the boundary of the channel, that is called your line canal. Okay. Or if you don't do anything, then it is called mobile boundary channel or non-erodible or unlined canal. Okay, or channel. Okay, so here we have different methods for both your line and unlined canal, or you can say erodible and non-erodible canal. So if you see from your exam point of view, or if you see for any competitive exam, this your mobile boundary channel or erodible channel is most important. Okay? You can find most of the questions related to your canal design is from erodible or mobile boundary channel. Okay, that is your number two. Okay, when because we have soil erosion when it is a mobile boundary. Okay, then if there is, if it is not line, there may be some growth of small plants in the sides which obstructs your velocity. Okay, then the water is also carrying some amount of silt, and in due course of time it's deposited in the bottom of the channel. Okay, so then it is very difficult to remove those silt deposited at the bottom of the channel. First, second, it reduces the capacity of the channel. Okay, so that is why there is some disadvantages also for mobile boundary channel and some advantages also. Okay, so those things you are going to study in your irrigation subject. Okay, here we are going to study only how to design this channel, or how to design this mobile boundary channel, or you can say erodible boundary channel. Okay, so we will discuss both, but first we will discuss about erodible or mobile boundary channel. Okay, okay. So for erodible boundary channel, your first method is Kennedy's seal theory. Okay, your first method is Kennedy's silt theory. Okay, so those things we don't need to discuss, because when you go to the steps, we are going to discuss these things again. Okay, so next topic you write steps required in design by Kennedy's theory. Okay, or you can write like this: steps required to design a mobile boundary channel by Kennedy's theory. Okay, so this method is basically a trial and error method. Okay, this method is basically a trial and error method. So first, step number one. Okay, my suggestion is to you write down the steps. Okay, because we are going to solve numericals, then you have to follow the steps carefully. Okay, so before this step one, we should know the discharge for this particular theory. For this particular theory, we need discharge. Discharge should be known. Bed slope, definitely when you construct a channel, that bed slope is known. It depends on the topography of the land. Okay, so decided by topography, it's written here. Okay, then severe is nothing but critical velocity ratio. Okay, this should be known, and then this cutters nk should be known. So don't worry, when you go for a numerical, these things is going to provide you. Okay, now what we have to do when we design a channel, that means we are going to find out the parameter. One is the maximum depth of the channel. Okay, at maximum depth of the channel, and one is width of the channel if it is a rectangular channel. So these are the two parameters we need to construct a channel. Okay, before constructing a channel, we need what will be the depth of that particular channel and what will be the width of that particular channel. And if it is a trapezoidal, width needed. And then we also need the maximum depth of water of that particular channel, including the side slope. Okay, including the side slope. So these are the parameters we required for construction of a channel. So when we design, our aim is to find out what will be the maximum depth of that particular channel. Our aim is to find out what will be the maximum depth of the channel, what will be the width of the channel, and what will be the side slope for a trapezoidal channel. Okay, with known discharge, known bed slope, critical velocity ratio, and cutters NK. Okay, so step number one, it's a trial and error method. So first we have to assume a depth of flow y. Okay, suppose y is equal to 2 meter. It's just an assumption. Okay, first we have to assume a value for y. Okay, it's up to you. You can assume 1 meter also, 2 meter also, 3 meter also. It's up to you. Okay, then you have to find out the velocity by using this equation. Okay? Is it visible? You have to use this equation. Okay, to find out the velocity. So first step is to assume a depth of flow y. Okay, second, then you have to find out the velocity by using this equation 0.55 multiplied by m suffix r is nothing but your critical velocity ratio. Okay, multiplied by y to the power 0.64. Okay, this is Canada's theory. Okay, first you have to assume a depth of flow, then you have to find out the velocity. With expression is v equal to 0.55 multiplied by critical velocity ratio mr and multiplied by y to the power 0.64. Okay, this y is nothing but your assumed depth. Okay, this y is nothing but your assumed depth. Okay, then we come to the third step. Okay, so we got y value, we got velocity, discharge is known to us, so we are going to find out area in the next step. That is nothing but discharge by velocity. So discharge is already known. For this is also called as design discharge. For what discharge, maximum discharge, we are going to design that particular channel. So this value is nothing but your design discharge. Okay, so that discharge divided by velocity, what we have calculated by using this equation, you will get find out the area, cross sectional area. Okay, so this is the third step. First step is you have to assume a depth of flow. Second step is to find out the velocity using equation 0.55 multiplied by critical velocity ratio multiplied by y to the power 0.64. Okay, third step is to find out the area. Area is equal to discharge divided by velocity. Okay, so next, step number 4. Okay, so generally we consider trapezoidal channel. Okay, we consider trapezoidal channel. So if z value is not known, if z value is not known or given, assume z is equal to assume z is equal to 0.5 comma 1 comma 1.5, or maximum is 2. Okay, comma 2. Okay, so if for a trapezoidal channel, if z value is not given, then we can assume a value of z in between 0.5 to 2. Okay, depending on the types of soil. Depending on the types of soil. As you can see here, for loose soil, z value will be more. Okay, so if z value is not known, we can assume any value between 0 to 0.5 to 2 with respect to our types of soil in that particular locations. Okay, so for loose soil, your z value will be more, and vice versa. Okay, so you write down this step number 4. You write down this step number 4. Over. That is our step number 5. So this is nothing but your area equation of a trapezoidal channel. Okay, that we have already discussed in many times. Okay, this is nothing but your area equation of a trapezoidal. And this is your weighted perimeter. Okay, so in that area equation, if you consider a trapezoidal channel, okay, this is your width of the channel. This is definitely y. This is z. 1 is to z, so this will be your zy, and this will be your zy. Okay, so sum of the parallel sides, so this will be twice z, b plus 2z. This is b. Okay, b plus 2z, b plus twice zy divided by 2, sum of the parallel sides, sorry, plus b. Okay, sum of the parallel sides. Okay, b is the bottom of the channel, and your top width is nothing but your b plus twice zy. Okay, top top width is equal to top width. Okay, so if you add this 2 divided by 2 multiplied by your vertical distance, that is your y. Okay, so if you further simplify, you will get this equation, that b plus zy divided by, sorry, multiplied by y, because this is b plus twice z and this is also b, so it will be 2 here, then we will bring it out to, it will be cancel out, so it will be left out with this b plus zy multiplied by y. Okay, so this is the equation for trapezoidal area, and this is your parameter, weighted parameter. Okay, so if you see in that area equation, That area we have already calculated in equation, step number 3. Okay, so in step number 3 we have already determined what will be the cross sectional area for that assumed depth. Okay, so in that equation, area equation, your area is known z. If it is known, it's okay. If it is not known, then we are going to assume some value between 0.5 to 2 depending on the types of soil. Okay, then next is y we have already assumed in the first step. So from this equation we can directly find out the v value. Okay, so once you calculated the v value, you substitute in the weighted perimeter equation and you can find out the p value also. Okay, so from the area equation you substitute all the parameters and find out the width of the channel, that is your bottom width of the channel, b, capital B. Okay, once you calculated capital B, you substitute in the weighted perimeter equation and find out the weighted perimeter. Okay, and find out the weighted perimeter. Okay, so in first step we are going to assume a depth of flow. Then in second step we find out the velocity using the equation 0.55 multiplied by critical velocity ratio multiplied by y to the power 0.64. Then we find out the area. Then normally we consider trapezoidal channel. If the side slope is given, it's okay. If it is not given, then or it's not known, then we are going to assume any value between 0.5 to 2 depending on the types of soil. Okay. Then in the fifth step, we are going to find out the area. We are going to use the equation of area and find out the width of the channel. That is the bottom width of the channel. Okay, and then we find out the weighted perimeter of that particular channel. Okay, so after completing fifth step we will move on to the next step, that is our six nothing but we have to find out the hydraulic mean depth, that is area by weighted perimeter, that we all know. Okay, area we have already calculated, weighted perimeter we have calculated in a previous step, so we will substitute here and we will find out the r value. Okay, okay. Then step number 7, you have to again find out the velocity by using this equation. You kindly write down this equation. Okay, 23 plus 0.00155 divided by SB plus 1 by NK divided by 1 plus 23 plus 0.0015 SB NK root over R multiplied by root over R into SB. Okay, you write down the expression. multiplied by critical to assume a depth. Okay. See, in first step, we are going to assume a depth of flow. Then again, we are going to find out the velocity by using this equation. That is your 0.55 multiplied by critical velocity ratio multiplied by y to the power 0.64. Okay. Then we find out the area. Then we are going to assume z value. Then in fifth step, we are going to find out the width of the channel and weighted perimeter. Okay. Then sixth, we are going to find out the hydraulic mean depth or hydraulic radius by A by P. Then in seventh equation, we are going to find out the velocity by using this equation. That is your 5.18, equation number 5.18. Using this equation, we are going to find out again velocity. Okay. See, in step number 2, we have already calculated velocity, and in step number 7, again we are calculating velocity. Okay. Next is step number 8. Okay. Then we move on to step number 8. And what we're going to do in step number 8, if the velocity obtained in step number 2, that is, in step number 2, we have already calculated the velocity by using this equation 0.55 multiplied by mr multiplied by y to the power 0.64. Okay. So in step number 2, we have calculated the velocity using this equation. Okay. In step number 7, again we have calculated velocity with that equation. Now we have to check this velocity and velocity you have calculated in step number 7 is equal or not. Okay. So what is written here, if the velocity obtained in step number 2 is not equal to velocity in step number 7, then assume second trial. See, whatever the velocity we have calculated in step number 2 and whatever the velocity we have calculated in step number 7, if it is same, then we need not to do further. Okay. That it means that our assumed depth of flow is our required depth. Okay. So for that particular depth, we are going to construct or design that particular channel. Okay. If your velocity at step 2 and velocity at step 7 is same. If not, then we have to go for a second trial of y, that is depth of flow. So we have to assume another depth of flow, and you have to repeat till this step. Okay, understood? First we have assumed a depth of flow, then we have calculated velocity, then we have calculated area, then we assumed a z value. Okay, then we calculated width of the channel. Then as at the same step we have calculated our weighted perimeter. Then we have calculated r. Then again we are going to calculate velocity. Then whatever the velocity we have calculated at step number 2, if it is same at step number 7, then we are going to stop. If it is not same, then we have to go for a second trial, or we have to assume another depth of flow, and we have to proceed all these steps till step number 8, or till we don't get a similar velocity. Okay, this will be going on till we are getting a similar velocity in both the steps. Okay, so here it is repeat steps 2 to 8 until two velocities are almost equal. Okay, so you kindly write down this step number 8. Okay, so it is nothing but if the velocity obtained in step 2 is not equal to velocity in step 7, assume second trial value of y, repeat steps 2 to 8, means from step 2 to step 8 until two velocities are almost equal. Okay, before we proceed, I really want to tell you that this type of numericals or this type of problems we don't do manually. Okay, but here in your syllabus is there, so you should know what is the steps. Definitely, manually it's not possible. Okay, so during exam also you have to select one or two velocities. If it is coming up the same, sorry, you have to select one or two depth of flow or one or two trial. If it is coming same, then it's well and fine. If it is not coming, then you can left over there. Okay, because these things it is not possible to do manually. We use some computer or numerical methods, okay, to solve such kind of problem. Okay, in general, we use MATLAB software to solve such theory. Okay, because each and every trial you cannot assume a value and that velocity and it's equal to that velocity. Okay, but that computer can, he can run number of trials and he will directly give you that at what y this velocity will be same. Okay, so those things easily can be done in MATLAB software. Okay, over step number 8. Okay, so then we move on to step number 9. Okay, so till step number 8 we are going to fix our y value. What will be the depth of the channel? What will be the depth of channel? Okay, by the trial and error method we are going to fix the y value. What will be the ultimate y or depth of the channel, maximum depth of channel? Okay, in step number 8. Then what you do, find in step number 9, find actual b and actual a. So whatever the area and width we have calculated is related to your first trial for a particular depth, because we are going to repeat the trial, and for that particular y what will be the area we have to find out finally. Okay, area and width of the channel, the process is same. Okay, you use the area equation. So once you both the velocity is same, then you are also getting the velocity, so you can find out the area with this equation, and then you substitute here and you can find out the width of the channel, that is b, width of the channel. Okay, from the last trial. Okay, then we have to provide a value called fb. Fb is nothing but your freeboard. Okay, freeboard. So why we need to provide freeboard? Because suppose see this discharge is known to us. Okay, so we are going to design this canal for that particular discharge. Okay, then we are not going to take a risk, because if a discharge coming greater than this q, then it will be overflow. Okay, then it will be overflow from the channel. Okay, okay, though we are going to take the maximum discharge, or we are going to design that channel for the maximum discharge, but still in worst case, if a discharge come or release in that particular channel which is more than that discharge we have considered during the design, then there will be a overflow. So what we do, whatever the channel we are going to design, we are giving some extra to that particular channel. This is this is for discharge q. If some extra discharge is also coming, then it shouldn't be overflow. Okay, understood? So this part is nothing but your freeboard. Okay, this part is nothing but your freeboard. So how much you are going to provide this thing, is if your discharge or whatever discharge we have considered for designing the channel, it is less than 10 meter cube per second, then we are going to provide 0.6 meter. So this length will be 0.6 meter. Okay, that is y. Okay, this nothing but before it is y, then after this we are going to add y plus 0.6. Okay, that will be your new y after providing freeboard. This is your freeboard. Okay, this is the y what we have designed for q. If in a worst case, if discharge coming more than q, then it shouldn't overflow. To avoid that situation, we are going to provide extra, that is called freeboard. Okay, how much we are going to provide? If it is less than, if this discharge, if discharge is less than 10 meter cube per second, we will provide zero point 0.6. If it is greater than 0.75, sorry, if it is greater than 10 meter cube per second, we are going to provide 0.75, or you can say more than 0.75. Okay, so this is our last step. Okay, 10th step, we have to provide freeboard, or sometimes we also consider 25% of that y as a freeboard. Okay, but in this particular theory, that Kennedy's what Kennedy is given that we provide 0.6 meter when discharge is less than 10 meter cube per second, and when is greater than 10 meter cube per second, we provide greater than 0.75, or you can also provide 0.75. So this is the your Kennedy's theory to design a mobile boundary channel, or you can say erodible channel. If you have any doubts, then you can ask me, or we can move on to a numerical related to this. Our next topic is drawbacks and limitations of Kennedy's theory. So there is nothing to explain. Okay, so you can directly, I will give you this PDF. You can directly write down from here. Okay, we have 10 points, which is your limitations. By simply reading, you can understand. Okay, so we are going to end this. It's about to end this meeting. Okay, so in the next, we will take 5 minutes break, and then we'll start the next class, and then we will solve a numerical related to our Kennedy's theory. Okay, so there will be a just 5 minutes break. Okay, then again we start with this numerical of Kennedy's theory.